Good afternoon, everybody. Good to see you all. Welcome to the 8th week, which is the 15th day of classes. Nice to see you all. We're halfway through the semester at this point. It goes so fast, doesn't it? So everybody's back now. You're ready to get back into our math, right? Great. Do y'all remember what we were talking about last? I know you might have forgot. It's been a long spring break. Fractions. Raise your hand if you know something about fractions. Good. I knew I was in the right class. Okay, today we're going to talk about adding and subtracting fractions. So let's see if you recall fractions, and we're going to jump right into it. Please remember to sign the attendance sheet. It's coming around. Could somebody give me a fraction? I need two fractions. Somebody give me a fraction. Let's call it, it was Timothy, right? Was that your pseudonym? Timothy, right? Okay, good. Timothy, give me a fraction.
It's 1/3.
Great fraction. 1/3. Perfect fraction. Let's see. Kate, have you got a fraction?
1/2.
1/f? Good. How about 1/? Put a number under there. Good guess.
1/2.
1/2. That's a really good one. Okay, so I'm going to put both of those, 1/2 and 1/3. These are good selections. So the first off, I have a question is, do we even know which one is bigger? And how do we know which one is bigger? We've seen all this before. We're just reviewing it this point. Which one of these is bigger? Is it 1/3 or is it 1/2?
1/3.
That looks like 1/3, right? Why do you say 1/3? Think about it, Kate. Why do you say 1/3? Is it because the 3 is bigger than 2? Is that what you were thinking? 3 is bigger than 2, isn't it? But let's see what Timothy has to say. Timothy, what would you like to add to that?
Because it's a fraction, 3 gets cut up into smaller pieces because you cut it into more, and 1/2 is bigger.
Ah, so you're saying this 1/2 is bigger than this 1/3 because this one is broken into smaller pieces. I can see Melissa has a comment.
Yeah, I think that the one on the right gets cut into 2 pieces because the number 2, and the other one gets cut into 3 pieces. So the 3 is smaller. The 3 pieces would be smaller than the 2 pieces.
The 3 pieces would be individually smaller, even if it's the same piece of pizza, for instance. Let's see, Kate, it was Kate, right? Kate, suppose I was going to give you half of a pie. Or suppose I was going to give you 1/3 of the pie. That means I'm going to cut it into 3 pieces. Would you rather have one of those 3 pieces or one of those 2 pieces?
3.
You'd rather have one of the 3? That's interesting. Well, you guys were right that actually one of those 1 out of 2 was a little bit bigger. Even though the denominator is smaller, that means that the pieces are larger, and so 1/2 is greater. Good. This is just a review of fractions. We know this. We've been comparing fractions, even producing equivalent fractions for a while in this class. Even we've been adding fractions as well, haven't we? Well, today we're going to talk about how we add fractions that have unlike denominators. Let's do a quick review of adding fractions with common denominators. What if we had added over here, actually I'm going to do it over here. In the last class, we added something like 4/5, which was 1 fraction, and to that we added another 1/5. Does anybody remember how we did this? When we added those 2 fractions? Good, I'm glad people remember. Does anybody remember the area model that we used to do this? You remember that area model, Kate? Okay, good, Kate. Then I'm going to draw a candy bar up here. Okay? I'm going to use a candy bar for the area model. How many pieces is that candy bar going to have in it? 4 or 5?
5.
You got it. It's going to have 5. Okay, so I'm drawing a candy bar up here that has 5 pieces. 1, 2, 3, 4. There they are, the 5 pieces. And that's the denominator. That's the number of pieces that the candy bar is cut into, right? 5. Well, you're getting 4 of those pieces. 1, 2, 3, 4. Okay, and so there's our fraction of 4/5 represented as an area model, right? So you tell me, how am I going to represent 1/5 as the area model. How many pieces do I divide the candy bar into? Timothy?
5.
You got it, 5. Okay, so there's 5 pieces. And this time, how many pieces am I going to shade? Kate, do you want to try? How many are going to get shaded? 1, 2, 3, 4, there's 5. How many am I going to shade? Good guess, try it again. This is 1/5. How many are going to get shaded?
1.
1, you're right. Okay, so 1's going to get shaded. Okay, so now think about this. You ate 4/5 of the candy bar. I ate only 1/5 of the candy bar. How many pieces of the candy bar altogether did we eat? Let's divide this candy bar into fifths and let's count off. Here's 4/5 and here's 1/5. So how many fifths are there here? Timothy, do you want to try?
I think you ate the whole candy bar.
You think I ate the whole candy bar. You're right, because 4/5, 1, 2, 3, 4, plus 1/5 is 5/5, which is the whole candy bar. That's right, so we ate the whole thing, right? And so in the last class, we saw that 4/5 plus 1/5 is exactly 5/5, right? And of course, 5/5 is the whole thing, or 1. 5/5 is 1, right? And we also talked about how a way that we could think about adding fractions is when we add two fractions that have the same denominator, then we can add their numerators. Here's 4 pieces out of 5, here's 1 piece out of 5, and so 4 plus 1 is 5 pieces out of 5. Did we add the denominators, the numbers on the bottom, together?
No.
No. Did we add the numerators together?
Yes.
Yes, we did. So 4/5 plus 1/5 was 5/5, which is 1. That's fairly easy to do when the denominators are the same. Melissa, do you have a question?
How do you know, how does 5 over 5 become 1?
That's a really good question. Okay? That's a really good question. How does 5 over 5 become 1? Would anybody like to answer Melissa's question? Kate, do you want to try? Go ahead. Hard one to answer, isn't it? How does 5 over 5 become 1? I'll tell you what, talk about it for 5 seconds among each other, okay? Go, talk about it. Okay, Timothy, how does 5 over 5 become 1?
Because you have, if you had a candy bar and you had 5 pieces and you ate all 5, that's basically eating the whole candy bar.
That's a great way to explain it. If you have a candy bar that has 5 pieces and you ate all 5 pieces, 5 out of 5 of them, you ate the whole one candy bar. Oh, this is an active class. Melissa, do you want to add something to it?
With fractions, you divide the top from the bottom.
That's true. With fractions, you divide the numerator by the denominator. So this also represents division, and 5 divided by 5 is 1. This is great. You guys are on it. Kate, do you want to add something to it? Go.
Because if 5 and 5 are not here, they can mention it's 1.
It's a nice way to think about it. 5 and 5 weren't here. Maybe it was 3 and 3. That would also be 1, wouldn't it? Okay, let's continue now. We're going to go to the big part of our lesson today is going to be adding and subtracting fractions that don't have common denominators, that have unlike denominators. Now look at these two fractions that you gave me. 1/3 and 1/2. Do those have the same numbers on the bottom? They don't. No, they don't. What are the denominators?
3.
3.
What are the denominators?
2.
That's right. So over here, we are going to try to add 1/3 and 1/2, but how should we do it? That's the question. How should we add fractions when the denominators are not the same? You know what, in mathematics, sometimes we just have to try something. Let's try something. Maybe we'll be right, maybe we'll be wrong, okay? Let's do some attempts, okay? So, attempts. I mean, let's try something, really. Maybe we should do kind of like we did in the last time. So I have my 1/3 here, and I'm going to add to that 1/2. We have different denominators. We know we want to add the numerators, okay? Should we do it in the following way? Should we do 1 plus 1, which is 2, and then in the denominator, there are different denominators, so which one should we use? Maybe we think, well, let's use the bigger one, the 3, okay? which was, so we use the 3. Hold that thought, please. So 1/3 plus 1/2, could that be 2/3? Well, I'll tell you, there's something funny with this. Think about it. 2/3, isn't that just 1/3 plus 1/3? That's true, right? Like when we did it over here with common denominators. 1/3 plus 1/3 would be 2/3, right? So then that's impossible that 1/3 plus 1/2 is also 2/3. Okay, so that attempt didn't work. Let's try something else. Or maybe we would think, I'm going to move it over a little bit to have more space. Maybe we would think, okay, 1/3 plus 1/2. Maybe I shouldn't use the larger denominator, maybe I'll use the smaller denominator. So 1 plus 1 is 2, and so it's 2 over 2. 2/2. Well, that seems kind of funny, because I know that 1/2 plus 1/2 is 2/2, using the same denominator. But if 1 plus 1 is 2/2, how can 1/2, I'm sorry, if 1/2 plus 1/2 is 2/2, how can 1/3 plus 1/2 also be 2/2? That doesn't make sense, does it? So that must not be the way to do it. It's good we're trying something. And then there's an obvious one that we got to try. Let's just add both the numerators and the denominators. 1/3 plus 1/2. Maybe that was, so you tell me, let's add numerators and denominators, and what would that be?
2.
Timothy. 1 plus 1.
1 plus 1 is 2.
Okay. 3 plus 2.
5.
Okay, 5. Now look at that. 1/3 plus 1/2 is 2/5. Let me ask you,
That's smaller.
that's funny, isn't it? Which is bigger, 2/5 or 1/2?
1/2.
That's right.
1/2.
That's right. 2/5 is only 2 parts out of 5. So how could we take 1/3, add it to 1/2, and get something smaller than 1/2? That's even smaller than 1/2. Okay, so there's a problem there too, isn't there? Okay. Well, I'm glad we tried something. It's good to have some attempts. None of those attempts worked, did they? Okay. Let's try something else. How about the area model? You remember that model that we used? We've been using that in earlier classes when we were talking about fractions, we were expressing fractions also. We used it there when we had the common denominators. So here's the area model. Let's express 1/3 in an area model. Let's express 1/2 in an area model, and let's see if we have a way to add that, okay? So here's 1/3. We'll use our candy bar thing, right? The candy bar is the area. How many pieces is this candy bar going to have?
3.
Good. So this candy bar has 3 different pieces, and the whole thing the candy bar represents the whole, and the pieces represent the denominator there. To that, we're going to add another part of the candy bar. The whole is the candy bar. This one has 2 pieces. I'm slicing it horizontally for a reason. The whole is the same size, but the parts are different, aren't they? For the half, the parts are bigger. For the third, the parts are smaller. Now this is 1/3, so we'll shade the 1/3 of the fraction. This is 1/2, so we'll shade the 1/2 of the fraction. Okay, but now here we have a problem, and here we begin to see why it's difficult to add fractions that have unlike denominators. The sizes of the parts are different, aren't they? You see that? The sizes of the parts are different. And the reason the sizes of the parts are different is because of the denominator. It's because on this candy bar, although the whole candy bar is the same size, we sliced it into 3 pieces. This one, although the whole candy bar is the same size, we sliced it into 2. Wouldn't it be nice if we could slice the whole thing into the same number of pieces? Okay, listen, how convenient that 3 and 2, they have a common multiple. We could slice the candy bar into the same number of pieces pretty easily. What's 3 times 2? 6. And what's 2 times 3?
6.
6, that's right. So here we have this candy bar sliced into 3 pieces. If I now slice it into 2 this way, I've just broke that candy bar into 6 different pieces. And the number of pieces that are shaded is just the same. And so now we can divide the other one also easily into six parts. It has 2 parts now. If we cut it vertically, we can see 2 times 3, this is our area model, is 6. So now it has 6 pieces. Notice, did I change in any way the part that was shaded?
No.
I didn't, right? The same amount of the whole candy bar is still shaded, but now it's just, I doubled the number of pieces. In this case, right, in this case I tripled the number of pieces, right? No, I doubled. It was 3 pieces, I doubled that to make it 6. This was 2 pieces, I tripled that to make it 6. But this is still, so let's rewrite the new fraction. Can you see the new fraction that comes out of this? What's the denominator going to be, the total number of pieces?
6.
That's right, 6. And how many are shaded?
2.
2. How about this one over here? What's the total number of pieces?
6.
And how many are shaded?
3.
3, good. Now, what about these fractions? Can we add these?
Yes.
Yeah, because they have the same denominator, right? Timothy, do you want to try it? 2, 6, and 3, 6?
2, 6, and 3, 6 equals 5, 6.
You got it. Equals 5, 6. We can see that right here from reading it off of the candy bars. We could also rewrite a candy bar here with 6 pieces, right? And we'd say, okay, 1, 2, I need these 2. 1, 2, 3, I need 1, 2, 3 more. 5, 6, right? Using our area model. Okay, so let's think about what just happened, right? First step is we wrote the fractions using our area model. We wrote 1/3 and 1/2 using our area model. We saw that we didn't have the same number of pieces, so then we had to think, how could I cut the 2 areas so that they have the same number of pieces in them, right? And that's why I did the second cut on each of these so that we had 2 candy bars with 6 pieces. Now, I want to connect this to something that we've seen earlier in this class. These are equivalent fractions. Do you remember that? 1/3 and 2/6 are equivalent fractions, aren't they? Timothy, do you have a comment?
I remember.
You remember that? Yeah, with equivalent fractions. So let's do it in that way also, because I want you to make the equivalent between the area model and equivalent fractions. Kate, do you have something to say also? Go ahead. Not really? Okay, no problem. Just stay with us, okay? So let's do this. Let's do it by an equivalent fraction method. We added these two fractions using an area model. Let's do it using an equivalent fraction model. To do this, we will list the equivalent fractions with the fractions we're given, and let's see if we can find 2 fractions that seem to be comparable to us because they have the same denominators. So let's see, our first one was 1/3. 1/3. You remember, to find equivalent fractions, we take the multiples of the numerator and denominator. So maybe the first equivalent fraction would be if we multiply the top and the bottom by 2. Then what would that be? Multiply the top by 2. Yeah. 2, 6. That would be the first equivalent fraction. Let's multiply the top and the bottom by 3. What's another equivalent fraction?
By 3? 3, 9.
Great. Keep going. 3/9. What's another equivalent fraction?
Let's do 4.
To do fours.
4, 12.
There you go. 4 12s. How about one more?
5,
Uh-huh.
15.
Great. 5/15. Okay, so those are some equivalent forms of 1/3, right? We're looking for one that seems comparable to 1/2. So let's do the same with 1/2. Here's 1/2. Let's multiply the top and the bottom by 2. Let's find the first multiples of
Okay.
1/2.
2, 4.
2/4 is equivalent to 1/2. What's another one equivalent to 1/2?
3, 6.
There you go. 3, 6. Let's multiply the top and the bottom by 4 now.
4, 8.
There you go. 4, 8. Top and the bottom by 5.
You good?
Top.
5, 10.
There you go.
Oh,
Okay, 5/10. Timothy, do you want to try the next one? Top and the bottom multiplied by 6.
Oh. Nothing.
6 times 1.
6 times 1?
6 times 1 is definitely 6.
Okay, and how about 6 times 2?
6 times 2 is 12.
You got it, 12. So 6/12. So these are all equivalent forms of these fractions. Now look at the fractions in the line of equivalent forms with 1/3. Do you see one here that looks comparable to one of the ones down here because it has the same denominator?
3, 6. 2 3s,
Look at
2
that.
6.
Do you see those? How about 3 6 and 2 6? Those look like two fractions we could add because they have the same denominator, right? And do you see those somewhere else up here on the board?
Yep.
You got it. That's the ones we used when we did the area model. You see that? That's why we divided the candy bar. So it had 6 and 6. We were thinking about equivalent, actually it's the least common multiple of 3 and 2. But there's another one we could have used. Do you see another one up here that would have worked? One that has common denominators on the board here? Look at 2 more fractions here that have a common denominator.
The bottom one?
That's right. The number on the bottom is the same.
I think I see one.
Which one? Which one, Timothy?
Oh.
Maybe 4 and 12.
Yep. And what's the other one?
And the other one is 9
6 and 12.
Yeah. You see that?
and 9 and 9.
Well, in this case, well, actually, we don't have ninths down here. That's an 8 right there. We don't have any ninths on the bottom. But we do have 4. That looks like, maybe that looks like a 9. It's a 4.
It looks like a 9.
Yeah. That's so 4 twelfths and 6 twelfths. So we could have added that too. What is 4 twelfths plus 6 twelfths? I guess you can do that in your head probably.
10 12.
That would be 10 twelfths. That's right. So look, these are other forms that we could use to also add these fractions that have uncommon denominators. So we need to bring this lesson to a close. We saw 2 different methods today that we can add uncommon denominators. We didn't get to do subtractions yet. We'll have to save that for another lesson because of our time. We could use the area model and we could slice the whole into the same number of parts. Or we could use the listing equivalent fractions method and find 2 fractions that have the same denominators. Now, I want to give you one practice, okay? One practice problem where you do where you're going to add 2 fractions. You ready for this? Okay. Now, I want you to use either method. And in fact, I'm going to ask you, well, I'm going to put the problem up here and then you tell me which method you're going to use, okay? The problem I want you to try is I want you to try this one. This is going to be 2/3 plus 1/4. Okay? Try 2/3 plus 1/4. Now, Timothy, do you want to use the area model or the listing equivalent fractions model?
Area.
Okay, then you use area. Melissa, will you try the listing model? Great. We'll discuss it in a minute. Same problem, 2 different methods. Let's see how we do, okay? Did you guys have some time? You ready to talk about what you got?
Yeah.
Melissa, do you want to tell me how you did it?
Sure. So I used the list of equivalent fractions method.
Mm-hmm.
And so right here, what I did was I multiplied 2/3 by 2 with the denominator. Was it numerator and denominator?
Mm-hmm. Numerator and
Yeah, numerator. And I forgot that you multiplied the bottom as well. I thought it was just the top, so I had to mark off all those and then do it again. But so yeah, afterwards I did it right. I multiplied the top by 2 and the bottom by 2, and I got 2 6. And then I did the same thing with 3, 4, 5, 6, and then with 1 4, I multiplied it 1 by 2 and 4 by 2 to get 2/8, and then this continued on with 3, 4, 5, and 6, and I noticed that the 8/12 matched the 3/12, and so when I added those together, it was 11/12.
And you feel like you got the right answer?
Because their denominator match, so that was easy to add the tops to make that. Yeah, I think that's right.
That's very interesting. Let's see what Timothy did. Timothy, can you tell me about yours?
I wrote down the steps and how to do it. I made a few mistakes.
Okay.
And then I did it. I put these together.
What is this? What is this?
I put these candy bars together,
Mm-hmm.
and it made this
Mm-hmm.
and this one. And I wrote those fractions down and added them, and I got 11/12.
That's really interesting. So show me where your 3/12 is.
Is that this one?
My 3/12 is here.
Ah, okay.
Now can we move?
And your 8/12. Okay, it's that one right there. Okay. This is very interesting. I want to ask you another question. How did you decide to divide this by 4 and divide that one into 3s? That took some thinking, didn't it? How did you decide that it was going to be 12 pieces and 12 pieces?
I count.
Yeah?
After I counted these little boxes, I counted all of them together.
Very interesting. Okay. So yeah, so you counted them all together and you saw it was 12, right? I guess my question is, how did you, because you started with only 3 pieces, right? How did you decide that you should cut it this way into 4 different sections this way that would give you those 12? You just tell us what you were thinking, that's all. I just wonder how you decided.
I decided because I put these lines over top of these lines, but I didn't put this part on.
That's a good way to think about it. So you put these lines over top of that one, didn't you? Okay. That's one convenient way to find common denominators. In essence, what you did is you multiplied the 2 denominators together. 3 times 4 is 12. Okay. Kate, do you want to tell us about yours too? Okay. What did you do, Kate? I see this. Is that a candy bar? And I see that you cut your candy bar into, let's see, how many pieces? 8 pieces?
8.
Great. And how about this one over here? Is that one big piece?
I see 1, 2, 3.
1, 2. And that's why you have 3 written right here, right?
6, 7, 8, 9, 10, 11, 12.
Okay, so you got 12 pieces, and 3 of them were shaded, weren't they? That's great. Now, can you tell me what 8 plus 3 is? Do you think you can do that?
11.
11. That was great. Did you get a little hint? Okay, great class. We'll see you next time when we talk about subtracting fractions.